All right. So in the previous lecture, we started off with a time inhomogeneous Markov jump processes. And we saw that nothing much changes apart from the fact that one, now we don't look at duration anymore. We look at the precise times at when we achieve, at when we see the process settling in one particular state. And what we see the next is that we always have to care about, the times that we are jumping at. So here we only write when we started to jump from this, when we made a transition from this state I to the state I itself again, or for this, I would say from state I to the state J. And again, why? Because we know that this transition rate is innately for the time duration of H. So even if I write only S here, I already know that I am in state I or state J here at time S plus H. So I guess that's straightforward. And we look at the way we write Kolmogorov's forward differential equation, which is kind of similar. But in the case of backward differential equation, it is a bit not that similar. So what we got was something, right? Did I not write the backward differential equation? No, it's here, right? No. Oh, I guess I did not write the backward differential equation. Or was it after this? Yeah. So this is how our Kolmogorov's backward differential equation will look like for the time inhomogeneous case. So the thing that's changing is we have a minus here, and a very important difference is that now we're differentiating with respect to S, not P here anymore. So I guess that's important. And then we also had a look at the occupancy probability, which is the probability when we do not expect to leave the state that we are starting in. So we saw that it is kind of similar, but again, here we have to take integration into account from S to T. And why? Because the transition rates keep on changing as and when we are moving forward in time. So to account for that, we take integration. And then we saw some example from the healthy sick dead model. And today we'll see the integrated form of this particular model again. So let me just copy this. Yeah. Okay. And then we saw the similar stuff for this two-state model. And we saw some more notations. I guess this was previously discussed as well, so not particularly new. Yeah. But again, when we were given some more information, not only what state we are starting in, not only what state we end up in, but also some information about how much time we have spent in one particular state where we started off with. So if that is given to you, then you use this formula again. So again, very first thing that should come to your mind is that these are Markov models, right? We expect them to follow Markov property, which states that it doesn't matter how much time I have spent in a particular state for me to decide what's going to happen in the next transition that I make out of that particular state. So you see the probability here kind of stays the same. So it is still mu ij upon lambda I. But again, now the only thing that differs is this mu itself. These transition rates differ. And what will matter now is the time at which you make this particular transition. So if you already know that at least or till W, you were in state I, then you know for sure that you have made the transition to state J only after S plus W time. And that is why these are the transition rates that will be much more suitable for this calculation. And we saw its PDF and blah, blah, blah. But again, okay, yeah, so I guess we did not cover this. So if you see this PDF is something like this, and this can be just written, this whole bracket term can be written as lambda I S plus W. And this is what you have attached to it as the PDF. So if you have a look at the integrated form that we saw yesterday, this is what you have, right? And if you multiply this thing with the lambda I s plus w, and if you divide here again with the lambda I s plus w, you get something similar. So this is the density, this is the probability, and then again, this is the probability of the next when you go from L to J state. So there is some sort of a connection, but again, it's fine even if you forget about that. And if you just have a look at the timeline that we have drawn here, then I guess it does make sense that way as well. So what we saw was, first of all, let's say we have to see what kind of equation we're looking at. So this is integrated form of Kolmogorov backward equation. So because we're looking at backward, we make the jump first. So what you will do is you'll make the jump first into some another state, which is the intermediate state. And always remember, we never want our intermediate state to be equal to I. And this probability Pij comma T is for all the cases where I is not equal to J. And let's say if your I were equal to J, then you would have this Pi bar. I guess that I have written here in the case of forward. Yeah. So this will be true for the forward as well as for the backward case, this particular equation. And yeah. So again, going through the three terms that we have here, the first term represents the probability that you transit from state I to state K, and you are in state I at time S, and you transit to K by the time T minus W. So again, here when I'm talking about the states, there can be any number of variation in the states in between this S and this T minus W. But all I care about is that when I'm starting, I'm at I, and at T minus W, I find myself at the K state. So this is the probability. And then we make a transition from this state K to the state J at time T minus W. And then we expect to stay in the same state throughout till T. So I guess that is what we have. And again, this W is random and we don't know what precise value of this W is, and as it can vary. So we have to take into account all the possible sample paths, and which is why you take into consideration of all the possibilities of jump in between here. So the very first jump you could ever have is here, or it could be here as well. Oh, so I did not write this integral, I guess. What do you guys think should be there? What should be the limit of integration here? Should be 0 to T minus S, right? Because that is all the possible values of W that you can have. Any doubts so far? Anyone? Okay, so now let us try to write these integrated forms of Kolmogorov equations for the same model that we studied. So let me just paste it here. And okay, maybe even before we write the integrated forms, let us try to write the residual probabilities. Okay, so what I mean by that is, let us say if I want to figure out the probability given that at time S, I was in healthy state, what is the probability that I will still be in a healthy state by the time T? So that can be represented as such. And this is what, let's say, I want to figure out. So if I were to draw a timeline for this, I know that at S, I am in healthy state. And in time period T minus S, so this here represents the duration, right? Because this RS is the holding time. So the holding time is T minus S. So what you do is S plus T minus S, which is equal to T. So this is your end, and you expect to stay put in the healthy state. So every time throughout this, you are in healthy state. So this will be your line. This will be your reference line for this particular probability. Okay, so now what do you guys think I should write here? So today in the class, we will only be discussing these sums, and I would highly encourage if you will be, much more interactive, because now it's more about, did you understand what the formulas that we just studied? And I guess if we can do it for these models, so we'll study this particular model in depth, and we'll see how we can change certain things and to make it a bit more real. So as of now, this is a very simple model that we are starting off with. Okay. But again, what do you guys think is the probability that I will observe this particular thing?
PH bar S for time interval S2T.
Exactly right. This is exactly equivalent to PHH bar for from S to T. I can write it as that, right? All right. And how can I rewrite this thing in terms of the transition rates?
Will it be e raised to minus integration from s to t lambda I of t?
Lambda I of
T dt, yes, or u dt, u du.
right? You cannot use T because T you have here in the limits. Okay, so what is this I for here?
It will be h, right? Not I exactly.
Exactly right. It should be H because that I represents the state that this represents the force of transition out of. So here I'm looking at H. Exactly. That is correct. So what can I expand my lambda H U? This is the total force of transition out of state healthy. So how can I rewrite this thing as in terms of the information that I have here?
Sigma U plus mu U.
Right? This will just be sigma U, which is if you go to sick, and this is if you are dead. This should be mu and du. Exactly. So this is your final probability that you stay put in healthy state from time S to time T. Perfect. Similarly, you can do the same thing for the other cases as well. But now we can move into some, okay, maybe we should discuss this. I mean, there isn't much of a calculation here. So let us say if I ask you, what is the probability that you stay again for T if you are starting at state D? So without any calculation, tell me what should be the answer to this probability?
1.
1, right? Because once you are in dead state, you will be in that particular state forever. Not only for this much of time, but forever you will be. So this probability is just going to be 1 anyways. So I guess that is good. Okay, so now we'll try to rewrite the transition probabilities using the integrated form that we have just studied. Okay, so let us try to figure out what happens if I am at sick state today, and if I go to healthy state, and the timings is this. So, okay. Now, first of all, I guess the very first thing that we should always do is to draw the line, right? So let me draw the line here. And I want you all to tell me what I should write. What I should write here is S T. So here I am at sick state, and here I am at healthy state. Okay. So what is now that I should do if I tell you guys that I want to look at the backward equation? So what I care about is backward equation integrated. Yeah. So what do you guys think I should write here? Or where do you guys think I should make markings? So maybe I should go back first to give you guys some. Yeah, so this was the graph we had, the Kolmogorov's backward equation, and just have a look at it once. And you'll have to use this particular formula to determine what's going to happen in there. So now let's say if I am here. So what do you guys think I should do next? First, we'll complete this line here. So go on. What do you think I should do here? Anyone? I'm not talking about the integral form. I'm only talking about the line that I have represented here. So what do you guys think should happen here?
You should draw the jump at the start of the timeline.
Okay, so where should I draw that jump?
Suppose at time interval, small time interval s plus w or s plus h, anything you can name that.
Yes.
And we should name the state
And what is the state?
L.
L. Okay. And what should I do next?
So from state S to L, it remains in sixth state only, right?
Yes. Okay, so now tell me one thing. Can I, okay, yeah, so go on. I want you all to think through this from start to the end. What should I do next? Okay, so now we have the number line. And now what should I do next? What should I do next here? I'll have to write the integrated form now, right? Okay. Savri, are you there?
Yes, ma'am.
Can you explain me what I have done here once again using this diagram? So what I want you to do is just explain me these three elements that we have here.
Ma'am, the integration we are doing it for the discrete, continuous time. So we are calculating the small interval from s to s plus w, like the time interval between that. So we are taking that integration, and for mu I from mu IL we are calculating the transition rate from from the time state s plus w, and then we are calculating the probability from L to J, like the probability that it will go from L to J from time in time s plus w to t.
Okay, good. Okay, and then we summed it up across over all the possible values of intermediate states that we could have, right? And we also integrated it over for the W. All right. So now that we have revised it, what should I write here?
It will be summation from L not equal to S, like summation of L not equal to S.
Let me just change the color. Yeah, summation L not, oops. Is it L not equal to S? Oh, okay, sorry. I thought S was the sample space. Oh, sorry, you meant S as in the sick state. Okay, yeah. So L not being equal to sick state, yes.
Then integrating from 0 to t minus S.
Good.
Then e raised to minus integration from S to S plus W. Lambda
Yes.
S u du.
Great.
Then mu SL S in bracket S plus W.
Very good.
Then T SL in bracket S plus W to T.
P.
SL. No. It will be L to T. L to T.
H, right? We're talking about
Yeah,
the
sorry,
states.
yeah. H.
Yeah.
S plus W to T.
Perfect. Okay. This is very good. This is precisely what we need. But there's one mistake. What else do we need to add here?
DW.
Thank you. Yes. DW, right? Perfect. Now can we simplify some terms here? So basically now that we have written the whole structure that we have, the very first thing that we will now want to do is figure out what all intermediate states are possible, right? So the very first thing that you can do is look at what states you can ever go to H from, right? Because this probability, if it's 0, then there's no point of considering that L as the intermediate state. So the way you can reach healthy state is only if you are at sick state, right? Does this make sense? So what all possible values of L do you guys think can be there? So I just said that this L to H should, I mean, this probability that you go from state L to state H should be positive, right? Not zero. So I said that this is positive only for the case where L is S, which is if you go from sick to healthy. Is this statement true? Is that the only case that is possible? Or is there any other case which you guys think is possible?
Ma'am, can you repeat what you just said?
Okay, so what I am trying to understand now, once I have written the whole structure, now I want to substitute in all the intermediate states that are possible, right, for me in this particular transition. So when I'm writing this possible values of L, what I want to make sure is that this probability does not become zero, right? Because if this is zero, then there's no point in considering that L. So what I'm saying is that the only case where this particular probability will be positive is if this L is S, which is if I go from sick to healthy state. For all the other possible values of L, this probability will be zero. Is this statement correct?
Ma'am, L can take H, right?
Exactly right. This is what I wanted to hear. Because sometimes what happens is we look at these arrows and we only see, okay, S to H, yeah, and then that's all. But again, that would have still created a problem, right? Because our L cannot be equal to S. So now what we will do is, we know if my L cannot be equal to S and D to H is zero, the only thing that I can have here instead of L is H. So this summation is no longer required, and all I can do is rewrite this thing. So this will still be e raised to minus S to S plus W. And instead of lambda SU, can I write something else here? I can write the whole transition out. So rho and nu. So this will be rho of u plus mu of u du. And instead of mu, S to L. Now I know that I'm writing for S to H. So again here I should maybe just write, we know that L is equal to H is the only possibility. Therefore, now this mu S to H. So what is S to H? It's rho again. So what you will have here is rho of S plus W. So you make a transition from sick to the healthy state at S plus W time interval. And then you stay in the H state, S plus W comma T D W. Does this make sense to you guys?
Yes, ma'am.
Any doubts with this? So again, just some another way you can rewrite this thing. If you do not want to write this whole e raised to stuff, you can also rewrite this. So this can be written as P, and you're going from S to S. I mean, you stay in the sick state, right? From what time? From time S to S plus W. And this will account for this whole big term. And then you can just write it like this. Yeah, that's it. So, well, yes, this is how you will write the integrated backward equation for sick to healthy state. Good. But now let us do the same thing for the forward equation. How would the forward version of this look like? So now what I care about is integrated forward equation for the same stuff. So P S H S comma T. And now I want you all to try, if possible, to not go through 1, 2, and 3 steps. Maybe just try to consider what's going to happen. Okay, first we'll have to draw the line, right? So I don't have space here, so I'm just going to do it here. S, T, H, S. Okay, what do you guys think I should add in here now? So that this is ended for the forward one. Anyone? So let me just draw the number line here, I guess. So I'm at S, then I'm at T, and here I'm at healthy state. Here I start off at 6 state. Okay, so what is it that I want to do now? So I care about the, okay, so first question, when are we going to jump in this case? If I'm looking at the forward equation, when do I expect to jump?
At the end.
At the end, right? Okay, so what marking will I have to do here?
It will be T minus H or W. Small T.
Exactly right. Yeah. So let's just stick to W. So I'm going to have T minus W. Perfect. And now what you should try to do is, see, previously we stated just some L here, right? But now you should clearly just have some idea. So, okay, going back to the previous thing that we discussed here, whenever you write a L here, without even writing these equations, we should try to think that I'm going to make a transition from this L to H, right? So what will possible L I can ever have? So instead of writing L here, you just write S minus S comma H, right? Because you know if you are dead at S plus W, you can always be healthy at time t. So I want you guys to directly tell me what should I write here? What is the intermediate state that is possible as a stop between this S and this H?
S.
S, right? And why did you not say H here?
Because in that state, we can't have the state where we are ending the process. Like
Exactly. Right. So here what was the concern is because we are making a jump and the jump cannot be to the same state itself. This L couldn't be S. And here when we're making the jump again cannot be equal. So this cannot be equal to our end state here, which is H, where we expect this process to stay for this time. Right? Okay. So now tell me, what should I write here? The expression here.
Ma'am, so the final one, like above you've written
Anything.
PSS thing.
Yeah, any of this or this is fine.
Yeah. So it will be something like integral 0 to t minus s.
Yes.
PSS bar, or will it not be a bar?
There will not be a bar, right? Because it doesn't matter if it stays in the state or not.
Yeah, exactly. Okay. And then in the brackets, s comma t minus w
Perfect.
into mu sh
Mu of what?
mu of t minus w
Yes.
into pss bar into brackets t minus w comma t dw plus pss bar s comma t.
Okay. All right. So this is not entirely correct. So Isha will try to figure out what are we missing here, right? First of all, what is this mu transiting? I mean, which states are you transiting from and to with this mu?
That will be sh, right?
SH. Very good. So then can I start at S here if
Oh
I'm
no,
ending in H?
no.
So should I erase that term?
Uh,
Let's do this part again, right?
yeah.
And again, can I just write instead of mu SH, I would just want to write sigma. Is that sigma? S2H? No, it's rho, right? So I'm just going to write rho here. All right. So what should happen next? Okay, so maybe what will help is whenever we draw this transition diagram, you know that at t minus w, let's say, I mean, the intermediate state is S, you can again draw some curve here and say that you land up in state H, because this transition rate will allow you to end up in the state H here, right? And then you stay in this state for the rest of the time. So what you have here is P H bar T minus W to T and dW. Does this make sense?
Yes, ma'am.
To the rest of you? What
So
about
the
others?
row, is it okay if we don't write sh since we are already specifying row?
Yeah, exactly, right? Because rho represents that transition
From S to
force
H.
from S to H only.
Yeah.
So I guess, and see, the thing is here, if we represent transition, if we represent general transition rates with mu, it's important for you to write these states. Otherwise, it would be interpreted as this mu, right? If you just write mu in the bracket time, then it would mean that you're going from healthy to dead. Or else you should write in the subscript to they say that this mu is actually the generalized version of any transition rate from S to
But
state N.
is it okay if I write row SH, because it really helps to visualize, right? Like SS, SH, and then HH.
See, you can write it, but then what you should do is you should redefine all of these transition rates in the beginning of the question. You can just say that, for my simplification, I'm just going to write sigma T as sigma H S T.
Okay.
Because then the examiner might get confused. So if you are looking at it from the examiner's point of view, they would have in their answer sheet something like this, the rho T minus W.
Yeah, yeah, yeah.
They might, so I guess just to be on the sure
Hmm.
side,
And anyway,
you
since we are
can,
going to be typing all this, I think it's fine if we don't write SH.
yeah, I guess, see, once you even write as such, you can erase it, right? You can just,
Yeah,
erase-
yeah, yeah,
yeah,
yeah. Right.
you'll be fine with it.
Yeah.
All right. Anything else? Okay, so now this was for the case where we could only have one intermediate step. Now let's try to analyze something else. So I'm again going to ask you guys the same question. I want to see what happens if I go, so let us do it from sick to dead. Okay, so guys, I'm deliberately trying to take examples which are not there in your book, so that what you can do is you can try to solve the other examples and actually verify your answer from the book, if it's correct or not, and see what you might be missing out. Oops, I wanted to take sick to dead. Okay, and we start at time S and we end up in dead at time T. Okay, so this is what I want to do. And now we can use any equation that you guys want. We can do it using backward, we can do it using forward as well. So anything. So let's just draw a number line. S time T, sick, I'm dead. So do you guys want to do this using backward or forward? Which one do you guys prefer?
Forward is better.
Forward is better. All right, let's do it using forward. So what do you think I should do here on the timeline now?
Same thing, we'll take a T minus W towards the end,
Yes.
and then there will be a jump from S to D. No, at that point
So
itself,
you
like the
mean,
same place thing that we did.
is this what you mean?
Yeah,
Okay, and you mean that there will be a jump to D
yeah,
here,
the
right?
same. Yeah.
All right, all right. And why do you think that only S should come here and not healthy?
Mm. Because we are assuming that it will stay in the same state, right? It won't make any transitions in between.
You mean from this to here?
Yeah.
Is that what we did? Let us go back to the, yes. Is that what we did? Check once.
Oh, that was for backward.
Yeah, right.
Yeah.
So always remember, we stay in the same state whenever I have this short interval, right? So for this shorter interval, I would stay in the same state. In the backward case, this was the shorter interval. So I would stay in the same state first, right? Okay, so now going back, what do you guys think are the possible intermediate steps here? I can have H here as well, right? I can also go from healthy to dead, right? So previously, the reason we only had this S here, because if we put D here, then there was no way I could go from D to H, right? So that is why I didn't put a D here. But here, now even if I put a H here, I can go from healthy to being dead as well, right? So I can make transition from sick to healthy, sick to dead, sick to healthy, healthy to sick, and then again maybe sick to healthy, and then sick to, and then healthy to dead, right? So there can be any possible variation that you can think of, wherein in the first case you will end up at sick state in time t minus w, or at healthy state in time t minus w. So these are two possible scenarios that we can have. So these are just the two possible values of L that we can have. Does this make sense? So these will be the two possible sample paths by which you expect to be dead. So maybe if you can't see it through this, we can go to, the very basic equation of the forward, and then we'll try to determine it using the three-step method that we did here. Okay, so let us first rewrite this particular equation for the forward case here. Sorry, Mihir, would you like to do that?
Yes, ma'am.
Go
So
on.
first summation for the values H and S.
Okay.
Then integration 0 to t minus S. Then PS, and then I think we should name that thing K is equal to H and S. So for the time period, S to t minus W.
Yes.
And then mu K to mu K to death D for the time period starting from t minus W, so starting time. And then it should remain in that point. So should I tell in the form of integration or that bar thing?
Anything.
So e raised to minus t minus W to t. Yes. Yeah, and then lambda is lambda. I think it should come d lambda d u du, and then tw.
Perfect, right? Anyone would like to suggest any changes in this? If not, we can try to simplify this equation, right? Okay, tell me if you see any error in whatever we have written on the board, and if not, tell me what should I write next.
Ma'am, if we are writing lambda d, there is no force of transition coming out from D.
Okay, why do you think that is the case?
Because if we are in state D, we remain in the
Yeah.
state D itself.
Right. So anyways, that would be 1,
Yeah, ma'am.
right? Because very good. So what is this?
It should be 1.
So this kind of represents P d d bar T minus W to T, which is always what? 1, right?
Yes, ma'am.
Okay, so that's just going to be 1. And for the rest of this, I can just maybe expand this. So the compact way should be to write it like this. So here you can just say that, K is equal to H or S. But for now, I'm just going to write it like this. So let us say S to H in this times. And then because you have a H here, what you care about is mu H D, which is just mu E minus W. So here I've used the actual transition rate, and there will be 1 here, so dW. But there will be another term which I'll have to add. So again, 0 to T minus S, P S to S comma T minus W. And here I go from S to D. And what is the chance of that happening? I denote that as mu, right? So this is mu T minus W dW. Does this make sense to you guys?
Yes, ma'am.
What others?
Yes, ma'am.
Okay, so yeah, I hope this is clear. So again, so see, you just have to keep calm and look at the formulas and try to see what all thing is possible and just do it. Otherwise, if trying to see what possible values of L you can have, if that is a bit confusing, then you can just write it like this and then basically have this would be easier because you have only 3 states here. But as if you are given 5 states or more than that, then it's very difficult to basically write this down for each of these possible states and then check for which this is 0 or if any of these terms become 0. So you should get used to trying to just see it, what L is possible in the cases of forward as well as in the cases of backward. Okay, so I guess I should just want to make this green. All right, that is it. Okay, so this was kind of good, but sometimes, so this was a simple case for the integrated equation. And now, let us say if you are given some more information, like, okay, so even before I say what information we have, maybe I can ask you guys a question. Does it seem reasonable that every time I become sick, my rate of becoming healthy again stays the same and only changes with my age? So here we have T, right? Ideally, it would be your age. Okay, so the time and the age goes on from 1 to 1 if I measure time in years. So just consider this T as, let's say, a year. So what do you think? Does the probability of you becoming healthy if you're sick today depends only on the age, or does it depend on something else as well?
We can say that the number of times I become sick again and again, that way rho will keep on reducing.
Exactly right. So the number of times, let's say if you're transitioning from sick to healthy more often, then your rho is likely to be less. Is that what you're saying, Isha? So your subsequent rows will be lesser, right? So the value of your row will keep on decreasing. That's a very good observation. What else? So again, I mean, just to break it for you guys, it will also depend on how much time I have already spent in the sick state, right? If there's, let's say, 3 years of time that I have spent in the sick state, then I would expect this row to not be the same for someone who is as the same age as mine, but has spent less time being sick. Does this make sense? So let us say if me and Isha, we are let's say of same age, and if I'm sick for 3 years and Isha is sick for only 1 year, what do you guys think? Who will have the higher probability of becoming healthy?
The person who's been sick for a lesser time.
Exactly right. The person who is being sick for the less time. Exactly. So now we'll try to incorporate that scenario into the model that we are looking at. So what I'm going to do now is, instead of just figuring out the probabilities of what happens in one state to other state, we also have information of how much of time a particular person has spent in some particular state. So this is something like, you know something about the holding time. So let us say I have a probability that I was healthy at time S, but then by the time T, I find myself being sick. But I also know for a fact that I have been sick. I mean, I'm sick not only at T, but I have been sick for at least W time when I find myself being sick at time T. So maybe let me just write it here. This just says that when I find myself sick at T, I have been sick for at least W amount of time. So just to give you guys an example, if let's say I'm drawing a number line, so at S, I'm healthy, and at T, I'm sick, right? So what I'm trying to say here, so this CT denotes current holding time. So let me just write, this is current holding time. Okay, so previously we used to talk about residual holding time, and now again, why do we say here that this is current holding time? Because this is where I find myself at. I mean, this is the end probability that I want to figure out. And what I'm saying is that, okay, I find myself in sick state at time T, but I also know for sure that at least for W amount of time, I have been sick. So if I go back W amount of time, let's say, and this is where I find myself, so this will be T minus W. So what it says is that you are sick from this amount of time up until this amount of time. Does this make sense to you guys? So if I'm talking about this CT being greater than W, what I mean is this particular thing. So again, what's happening here is I have assumed that my CT is equal to W, right? What I have done is I've just written T minus W here. So I'm basically assuming here in this particular scenario that I have been sick at least not I have been sick for W amount of time. If I have to talk about at least W amount of time, then I know for sure that this is the minimum I'm spending being sick. I could be here, I could be here, I could be here, I could be here as well. So if that is the case, which is what we're trying to do here, you will have to use some another random variable to denote this as t minus v. So when I write t minus v here, this is the actual time. This is the actual time you became sick. And then stayed sick till time t. So just to make our analysis better, this is what we'll have. We'll introduce this another time, which we do not know, right? Because the only thing that we know is that this current holding time is greater than W. So it could either be this W, it could either be this, it could either be this, or it could either be this. So this T minus V is the thing that is varying now. Does this make sense to you guys? So do let me know if you get stuck with any of thing that I'm trying to explain now. So now what I'm going to do is I'm going to try to write an equation for this guy here.
Ma'am,
Yes, Isha.
so you're saying that suppose in the sum they have given that W is some time, so it won't be that I have been sick since W only. So I could have been sick before that also. That is what you're trying to say, right?
Yes, right. Because we are given that CT is greater than W. We don't know if it is equal to W plus 1, W plus 2 or what, right? It is greater than W for sure. And again, because we are measuring time. So again, let me just write here that W is the duration of time. Okay, W is a duration. So for W time, so this W here is duration. Okay, good question. Anything else?
No, ma'am. I thought W was some age or something like that.
Yeah, I sense that. Very good question. All right. So that is why W. So, okay, whenever I'm talking about the holding time means the time I have spent in a particular state. So this W is the duration at minimum that I expect to spend in the state S by time T. So I know that this could either be this or anywhere from anywhere else as well, basically. All right. So now we will try to write the equation for this guy. So let me just put some integral for now. I'm not going to write its limits. And the very first thing that we can do is we can see here clearly that the only possible state here is what? Can anyone tell me? So again, I cannot be dead and then be sick again, right? So the very first case that we will look at is PHH. So the probability that I am healthy at time S and that I am healthy. So I find myself here. So when I am at T minus V, when I make a transition to the state S in actual, right? So here what's happening is I know that so what is my T minus V? T minus V is the actual time when I become sick, right? So you cannot, you can be sick somewhere in the between here, but then once, let's say if you become sick here, you are again becoming healthy. Once you reach T minus V, you are sick forever till T. So this is the time when you become sick for the rest of the time, okay? And that is why here, you cannot have an intermediate step here from where you are jumping as S, because then this time wouldn't be T minus V, it would be this, right? So here the only possible intermediate step is H. So that is why I write that I am at H in time S and I am at H in time T minus V. And then I make a transition from healthy to sick, which I'm denoting as just sigma. And this transition happens at time T minus V. So this is a transition from H to S. Okay, at T minus V. And again, the reason I have H here is because if this were S, then T minus V is not the actual time after which I stay sick till T. Okay, so now I have jumped to my state S at time T minus V. And then I stay in the state S forever till T. So I will have e raised to minus integration T minus V to T. And here the transition rates out of sick state. So again, a row, if you become healthy again, and sorry, I mean, I shouldn't say if you become healthy again because we have a minus here. So we cannot be healthy. We basically just stay sick. But this is the force of transition out. And now, if you see, we will not be integrating with respect to dw. We don't have any w in here, right? We only have v. So we'll be integrating with respect to v. Because w does not anymore denote the thing that we have taken by our own. W was given to us as the minimum time that we expect to be sick before time t. So this is just the minimum, but we could be sick anywhere here as well. So now I want you guys to think about what should be the limits here. What is the minimum value of V that you think my probability into consideration will have? What is the minimum value of V?
It cannot be 0, right? Because we already know that at S we were healthy. So will it be some very small amount of time?
Okay, and why do you think it should be a very small amount of time?
Because that is possible, right?
Okay. Something else. Let me ask you one question. What does my V denote? What does V denote?
V will be the time we were healthy.
The time we were healthy? Why do you think? Okay, so Isha, if you mean that T minus V is the time we were healthy, are you trying to consider this here? Are you trying to consider this? But again, always remember that this is a probability, right? This is not a transition. So I can vary. I can be sick here. I can be healthy again. I can be sick and healthy again, and so on and so forth in between here. So this T minus V is something that we started off from here. We looked at this as our V, right? So if my T minus V is the actual time I become sick, then my V is the time I spend being sick before I reach T. Does this make sense? Does this make sense? So let's say if we forget about this V and W and all, let me just put some numbers to give us some perspective. So let us say my W is 4, okay, and let us say my T is 10 and my S is 0. Okay, so my S is 0, my T is 10, and what I'm trying to say is that I know for sure that from 6 to 10 I am in sick state, okay, but I don't know whether I was actually sick only for these 4 years or I'm sick from previous years as well. So the only thing I know is that my CT, my current holding time, which is, so again, remember the T here is same. So this current holding time corresponds to wherever you are in at time T. So this CT is greater than 4, which is my W, right? So you could have been sick at 5 as well. You could have been sick at 4, 3, 2, 1, anytime. But let us say if, so we're starting at healthy here, right? So if I go from healthy to sick, that's fine. I can again go and become healthy here. So what I mean by this orange stuff here is, let us say that 4 is the time. Wait, 1, 2, this is for 3, this is for 4, this is for 5, and let's say this is for 6. Okay, forget about the rest
Can
of
you
it.
just repeat the part after you explained CT greater than 4? There was a power outage,
Okay.
so I reconnected.
Okay, yeah. Yeah, so what I'm trying to say here is that this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, these are the years that I am looking at. So I'm not looking at the continuous time here. I've sort of made it discrete time. So I know that at my S, I am in healthy state, and at T, I am at sick, right? And I also know for sure that during this time from 6 to 10, I am sick, right? Because I've said that my current holding time is greater than 4. So this, I said something about this T being the same here. And because you have this T here, this denotes the current holding time of the state where you are at XT. So once you know that, okay, now let us just say that so this is the information that is given to you, okay, and now we are trying to figure out what happens if we want to figure out this particular probability. So this is W, you know for sure that you are sick for all of these time periods. Good. Now what else can I know? So to make these equations, the very first thing that we assume is, let us say that I know when I actually became sick. So when I actually became sick, so what I mean by actually becoming sick is when I actually became sick and then I've stayed sick forever. So I know that my CT is greater than W, but now I'm making an assumption that I know for sure that my CT is actually 5. Okay, it is not only greater than 4. I know for sure that it is 5. So you know for sure now that you stay sick up until 10 from 5. Okay, so now I'm trying to explain to you guys about the transition and the very reason why we have only H here and why not S. So let us say if at 4, I find myself at S. Okay, so we think that, we can go into the sick state from being sick and from being healthy, right? So these are the two possible intermediate steps that you would think you can be at 4. Okay, so let us say if we are at S, then what are we doing? We are making a transition from S to S again, and then we stay in the S forever. So ideally, my calculation of CT being 5 is wrong. It should be 6 because I stay sick from this time interval, right? I am not only sick from 5, I am sick from 4. But that is not what we have assumed. We have made an assumption that I am staying sick for this 5 amount of time. That is why you cannot end up at sick just before you make the transition to the sick state. So you have to end up at healthy state in time period 4. So that then you make a transition at 6 state, and this is validated. This does not increase in time. Does this make sense?
Yes, ma'am.
What about others?
Yes, ma'am.
Saudi and Swapnil?
Yes, ma'am.
Okay. Swapnil? Okay, I hope you said yes because I couldn't hear you, Swapnil. All right, so I guess this is clear. Okay, so the important thing here is now about the integrals for my V here. So now, Isha, can you tell me what will be the integrals here? What is the minimum value that my V should take?
W?
Precisely, right? It should be W because I know that W is the minimum time I expect to find myself in the 6th state up until time T. Very good. And what is the maximum value that we can take?
Infinite? No, sorry, T. The
T.
difference. The difference. T minus S.
Why do you think it should be T minus S?
Because that is the complete duration.
Okay, so can this
We
be
cannot make
precisely?
the transition immediately. So will it be T
Yeah.
minus W?
Okay, let's see what T minus W denotes. T minus W is here, right? T minus
Yes.
W is this. And what is my W? My W is this duration here.
Yes.
So what you are saying is that you start from W. So my V, so I'm measuring V backwards. Okay, try to measure V backwards. And then you will get some nice answer for it. So my V can at minimum VW, which is that my V can start from here. But then I know for sure that my V could go up until here, right? So in theory, it can never be at S, but it could go to a very, very near point to S here, right? So how do I measure this time? It will be something T minus S. So let's say if this is S plus 1, this would be T minus S plus 1, right, in brackets. Something like this. So this will just be T minus S minus 1. So in theory, because I'm assuming continuous time, it has to go to T minus S. Because I cannot write something like T minus S minus 1 for continuous time interval. And that is the reason why V goes till T minus S. So the minimum, so okay, starting from the start. What is V? V is the time I spend being sick before I reach T, right? And it was given to us in the question that for at least W time, you stay sick. So I know the minimum value I spend being sick before I reach T is W. But what is the maximum value I can spend being sick? It is if I take this to the extreme case here, right? So that the whole time I spend being sick, and then that will be just T minus S in theory. So it will never be equal to T minus S, but because this is integration, anything at equal to, the chance of that happening will be 0. So you take bars into account, you take a particular interval into account. We aren't calculating it at a point particular. Does this make sense? Let me raise this. So this was it. When we are given some extra conditions. Let me just put the heading here. Any doubts with this? Anyone? No doubts? Okay, so now what we will do is we will try to see another model. So this is where we were given some extra condition about the holding time of the state at which we end up in, right? So now these holding times could be different. So sometimes you might be given some information about, let's say that you were in healthy state. I mean, even before you are at healthy steadiness, you were already in healthy state for some particular time here. So this could also be given to you. So we'll have a look at that information now. So, and generally, why do I incorporate that sort of information in my model? Because I find that if a person is sick for more amount of time, then the transition from sick to healthy might not be the same as it would be for the other person who is of the same age, right? So now I'm going to redefine my model. So I still have healthy, sick, and dead, and there are transitions that I make. Okay, so what I do is this will still be sigma t, but this will no longer be just a rho t. If I make this condition that if I stay sick for a longer period of time, then my rho will change. So that will kind of not go along with the Markov property, right? Because what my Markov property says is all that matters to determine my transitions in the future is that I am at a particular state today, right? It shouldn't matter how much time I have spent in this state or how I have come to this particular state. What should matter is that I am here today and that's it. But here, if we say that the CT, which is the current holding time, also matters, then it kind of negates and it kind of doesn't go well with the Markov property. So what we try to do is, instead of changing the states, we change the transition rates. So now I am saying that my transition rate not only depends on my age, but it also depends on the time I have spent in a particular state. So that I automatically have different value of rho for different value of CT. And this will be only for the case when you go from sick to healthy, because we're assuming that if you're sick for a longer period of time, then this is ideally increasing. But I guess as Aisha said, if you have a particular, tendency to be healthy, be sick, be healthy, be sick again, then even this would be depending on the CT. So again, here I'm just writing CT because I'm assuming that I'm at state sick in time t. And here again, I'm not going to assume that the current holding time matters, but here I am going to assume, because if I am sick for a longer period of time, then I expect that person to be dead at a higher chance than someone else who has been sick for a shorter amount of time compared to the one that we discussed earlier. So this is the kind of model that we will have now. So let me just call this a model with duration dependence. So now my transition rates not only depend on the t, the time at which I make a transition, but also sometimes for some cases, the time I have already spent being in that particular state. Okay, so now let us say if I ask you guys, what will be the probability? This is, I guess, let's see what you guys answer. What is the probability that you stay in the healthy state from time S to time T? Will this change now that I have added this new information here? What do you think? Will this probability change or will it not change? Okay, even before we do that, can you tell me what should I mean, forget about the CTs that I have added now, or maybe you can take them into consideration as well and try to think what will be the value of PHH bar ST. So this is something like the occupancy, right? The direct formula that we have started. So what do you guys think I should write here?
So ma'am, e raised to minus s to t, integration s to t, and lambda h u du.
Right? And what is my lambda h here?
Sigma t plus mu t.
Sigma u.
Sigma u plus mu u.
Right? So the only transition rates that I have changed is rho and nu, which doesn't show up anywhere in this equation. So this equation is unaffected by the new additional information that we have now. Okay, so this is fine. But let us try to see what happens if we look at some probability which depends on that information. So let me just erase this. And now we will try to look at, okay, so now the way I write this equation is also going to be a bit different. So what I'm going to, okay, let me just first write this. So what I want to figure out right now is the probability that I find myself sick at time t. Let me draw this simultaneously. So I am sick at time t, at time s, and at time t, I find myself sick as well. So something Rs greater than t minus s, given xs, s, cs, w. Okay, so let me not draw the number line for you guys. If this is the probability that I tell you to calculate, can you tell me how should my diagram look like? So let me just draw this here again. Okay, so let us say this is my S, and let us say this is my T here. Now you guys guide me about how should I write and fill in this time and states. So this is time. Maybe I can use a different color for state. Yeah. So what state should I write here at time S? Anyone? Quick. So this is the question. What state should I write here?
Sick.
Sick. Right. And what state should I write here?
Sick again.
Sick again. Okay. And how do I incorporate this information? Okay, what does this information tell me? Can someone explain me this in words? What does CS being equal to W mean?
So W means that for the W amount of time, it has remained the stick state.
Right. So how can I represent that on the line here?
Ma'am, your CS equal to W means that W is also equal to V, right?
Okay, we haven't yet talked about V. V is what we do once we have everything that is given to us in the question on the line. But we don't have that yet, right? So don't think about V. As of now, we are just trying to use all the information we have. So we know that at time S, I am in 6th state, yes. But now we have to represent this on the line here. So what this says is that the current holding time at S is W. So the holding time means that you have been in the same state as the state that you were in time S. So at S, you are in 6. So this means that by the time small s, you have been in the state, this state, for W time period. So if I go back here, so let me maybe just use some another color here. So if I go back W times, which is if I write S minus W here, and if this represents W time period, then I can say for sure that I was in the 6th state throughout this time interval. And this is what it means by CS being equal to W. Does this make sense? No? Yes?
Yes, ma'am.
Yes, ma'am.
All right. So when I'm saying that CS is W, Isha, what do you think? Are you still confused? You can ask me again. Isha, are you there? Okay, this may be some power issue. All right. So now that we have already incorporated this information, right? Okay, now let us see what this information mean, because this information is already incorporated here. So what does this mean? Anyone? What does RS mean? Okay, first of all, what is the difference between CS and RS? CS is my current holding time. It shows something about what I have been doing up until today. And when I have RS, it means the residual holding time. What's going to happen next? So when I'm talking about this RS being greater than T minus S, what do you guys think I might mean? Anyone? Can you guys guess? What possibly could be the meaning of Rs being greater than T minus S? So we know Rs is the residual holding time.
Does it mean that for at least T minus S duration, it remains in the fixed state?
Yeah, it exactly means that, right? So when I'm saying Rs is greater than T minus S, it means that for at least T minus S duration, which is all of this, right? All of this, I stay being sick. So here, I know that for all of these, at least I am being sick. And I could extend beyond this as well, but I know for sure. So this is anyways calculating the probability that you are sick, right? And so again, what we want to figure out is what happens from S to T, but inherently we do know that we are sick from S minus W till T. Okay, so this is what is given to us in the question, and this is the kind of diagram that we will make first, right, when we read the whole question. Okay, so now how do we proceed further? What we always do is we create some intermediate step in between, right? So we care about something from S to T, so we will create some intermediate step in between there. So let me just use a darker color, and what I'm going to do is let me just define some intermediate step here, and the time is denoted by U. So I denote my time as U here. Okay, and again now we'll see, but again there will be no change at the intermediate step here because we expect to stay in the sixth state. So we'll see how do we represent that probability. So now this probability will be written as this thing. So what I will do is, again, this is something like SS bar, right? So I denote this thing as PSS bar S comma T. Good. But I know that now my rho, I mean, ideally what I would have for this is e raised to minus of integration S to T, then rho of U, something, something. But now my rho also depends on CT, right? So I'll have to see how does this CT change now. So what I will do is I will just rewrite what I would have. So e raised to integration of S to T. But now, whenever I write my rho, this thing is going to change now. So what I do is, I write a U here, and I will write just CU here. Let's just denote it as CU for now, and I'll have plus mu of U comma CU, right? And du here. So this u, which we have represent the time between S and T, could be anywhere, right? So that is what I mean. So what we want to care about is these transition rates. And as we know that these transition rates differ for each of the time that you travel in between here. So this u and du that we have is to account for the fact that these transition rates in between S and T do not stay the same. They vary with respect to the time that you are traveling at and transitioning at. Okay, but now what about CU? What is my CU? Can someone tell me what is my CU here? What does my CU represent in words? Anyone? What does CU represent in words? Sorry, what do you think CU represents in words?
Am I audible? Because
Yeah, now you're audible. I couldn't hear you.
sorry.
Did you?
Yeah. No, I was having some network issues, so sorry. Ma'am, CS
Okay.
was the time, like the probability that, not probability, but that the person is in the state, sixth state till like for minimum W. So CU also is similar. Like, is it the time? Like, sorry, just a second.
Yes. Take your time.
Basically, it is like that we will be in the state, whichever state till time U.
Yes, exactly right. So this CU represents what? Precisely, it just represents how much of time I have been in that particular state, right? So the time I have spent being sick, right? Before you. And this U is time. So now if I have to check that, what will my CU be? I just have to measure the time I have spent being sick, right? So what will that be? I know for sure that from S minus W, I am sick. So that will just be all of this time, right? This will be my CU. Do you guys agree with this? So now what I will do is, I will just, instead of writing CU, I will write U minus, okay, let me just do this in here. So what will my CU be? U minus S minus W, because this is the time I know I am sick, right? Continuously. So this is what I will have. And this just translates to U plus W minus S. So this will be your final answer. Does this make some sense? So, okay, now if you have a look at this, you won't be able to tell, right, that you were given some additional information that you were already in sixth state from at least from W times before S. So to incorporate that, what you do is you do not denote this thing as SS bar. You denote this thing as S, W, S bar, to take into account that you know that W amount of time you have spent for sure in the state at which you are in this time S. Sorry, this is state itself. So let me just say that again. So this SW here represents that you have already spent W time in sick state. So this is PSWS bar S comma T. So the one change that has happened here is that our state space is no longer discrete. It has become continuous because the way we hop on depends on the time that we have spent in that particular state. So that is one reason why we do not split the states. Because had we done that, then you would have, I mean, you could have infinite states, right? Depending on every time you spend some particular amount of time in that particular state. So to avoid that, we have just taken CT in the transition rate so that our transition rate can vary now. And we only have 3 states, healthy, sick, and dead. And the change that we have done is we have incorporated the information that we know for sure that we are sick not only at time S, but we are sick from W time period before S. So first we wrote the same equation, but we incorporated the fact that these transition rates vary with respect to the current holding time. And then we substitute in the value of the current holding time. And what is my current holding time? It represents the time I have spent being sick before U. So this U is arbitrary again. This U is subjected to vary for any time from here to over there, right? So if it's here, then this will be again U minus S minus W. So this much of time you have spent being sick. So this CU increases as in when you move towards T. Does this make sense? See, because my S and my W is fixed, right? And this U is what is changing. And this keeps on increasing. And this U is some time here. This is not duration. So let me maybe just write that U is a particular time. So whenever I put a dash here, it means that this is time. And if I draw some interval symbol here, I know that this is the duration, this is the duration. Does this make some sense? Okay, this is actually the last thing that we're doing today. So just bear for like 5 more minutes with me and then we'll be done. So now I have this, and another way to rewrite this particular equation would again just be, let's say if you change this U from S to T, and let's say if you add S everywhere we have U here, so then you'll subtract S from here. So you have T minus S, 0. And here you'll have row of S plus U, and here if you add S, you'll only have U plus W plus row S plus U, comma U plus W, and here you will still have DU. So the way to interpret this particular equation will be that this S plus U, what is this S plus U? This S plus U is the precise time when I'm making a jump. Is this the precise time when I'm making the jump? Not anymore, right? Because I always make the jump at U. And this was the time when which I have used already in this equation. So here when I have S plus U, this S is here and this U is here. So you should decide for yourself which of these equations you feel more comfortable with, and you can choose to use any of these. So here S plus U here it's just a bit of confusion because we've seen U as one particular time. But if you forego that and if you look at U as the time difference, so let me maybe just say something here. Let me just highlight that here we have T minus S, right? And that is what the value of U is from 0 to T minus S. So here this U represents the difference. And we know the minimum difference is 2 and the maximum is T minus S. And the U that we have here, which is from S to T, this represents the actual time. So you can choose to basically use any equation that you feel more comfortable with. So these are two different ways you can rewrite the same probability. So I hope that is clear. Any doubts so far? Anyone? Okay, so now let us just try to solve one small example so that we see how much of this we have understood. Okay, so now what I want to figure out is the probability that at time t I am healthy given that at time s I am in state sick and my CS is W. Okay, so here this is, yeah, let's try to solve this. I would say this is a good. So what do we have here is probability that we go from sick state to healthy state, right? So we are going from sick to healthy, but we know that we are in sick state for at least for W amount of time, right? So, and again, time is S to T. So this is what we are trying to figure out. And let us try to draw this line here. Okay, so we have S, we have T. At S, I am in sick state. At T, I find myself in healthy state. Okay, and I know that I have been sick for W amount of time. So if I write S minus W here, I can write S here. Or maybe what would be more appropriate is to just say that I am in sick state for this interval. All right. Does this make sense? Can you guys hear me? Hello?
Yes, ma'am.
Yes, ma'am.
Okay, good. Thank you very much. Okay, so now what do you guys think I should do next? So I have already written every information that we were given on the board, right? So what should I do now? Okay, I guess maybe I should do this example and then you can do another example so that you can again see the way we use the logic here. Okay, so the very first thing that I want to do, so what I will do is I will try to write my answer and then I will see what all stuff that I need. And then I will see what all, should be happening. Okay. So the very first thing that I see is that I am in sick state from S minus W to S. This is given to me. But again, this does not concern me because what I'm concerned with is what happens from S to T, right? So I know if I'm sick here, if I'm at state H here, the possibilities in between is that I can be sick or I can be healthy, right? There are two possibilities that I can have. So the very first thing that I will do is I will make some intermediate state here and I will declare, okay, so even before okay, so let me just not put that far. Let me just declare some intermediate state here, which is at time U. And this measures the time I spend being sick. So again, before I go to some another state, which could be healthy only, right? Not dead. So again, if I am at sick at time S, then I'm just stating U as some time till when I stay sick from S minus W to U. So I know for sure that I stay sick up until this much of time for sure. So I can rewrite this thing as e raised to minus integration of S. So again, you might be tempted to write S minus W here, but all we care about is what is happening from S. So I have this thing from S to U and I'll have rho here. So I know what is changing here. So I think I can so I shouldn't be writing U here. So maybe I can just change this variable and make this variable V, right? So I'm planning to change this to V. Okay, and I'm writing just U here, okay, and now what will be my time that I spend? That will be W minus, okay, so maybe even before we do this, what else do you think should happen here on the line? Can someone see? To write how much of time do I spend in sick state, what else do we need? So again, let me just first write here. V is the actual time when you first leave the sick state. Okay, so this V here is the actual time when you leave the sick state for the first time. Yeah, when you first leave the sick state, or when you leave the sick state for the first time. So this is same, right? So I know for sure that up until V, I was in the sick state, and then I transited to some another state. So what all state I can jump to from sick and then try to be healthy at time t? The only possibility is H, right? So I can only jump to being healthy so that I can again be healthy later on. So I guess what you will have here, so let us for now ignore, we just write this thing as Cu plus nu u comma Cu and du. All right, so this is what I have for the times S to V. Okay, so now what is happening next? At V, I make a transition to be in the state H. So what I'm transitioning from sick state to the healthy state. So this thing will be multiplied by the transition rate, which is rho. Okay, I see this again depends on the time I have spent, right? So I will have V and CV. All right. And then what I do is I'm staying in the healthy state at time V, and I find myself in the healthy state again at time t. And again, because we assumed in this V arbitrarily, what we are going to have is some dV and some proper full integration from time S to time t. So this V could be actually anywhere in between S and t. So this is what you have. This is multiplication. I don't know how to write this. Maybe I can write a multiplication here. Okay, so now we will try to rewrite this whole thing. I have integration from S to T e raised to minus integration of S to V rho of u comma. What is my Cu? My Cu represents the time I have spent. Okay, so it's difficult for you to see where is Cu. So maybe you can just write some u in between here, which is the intermediate state that we take. So this, for us to just be able to visualize this, what will be my Cu? This will be the time that I have spent being sick, right? So it will be u minus this time period. So what I will have instead of Cu is u minus, oops. So this will be u minus S minus W. All right. So this is my Cu and plus mu u comma this again. So this is just u minus S plus W. And this is what you get with du. So this is in the power of this E term. Then you multiply this thing with this transition rate. So this is rho V comma CV. Okay, so now what is my CV? Can you guys see? Can you guys tell what could this CV be? Anyone? How can I write CV here?
It will again be from S minus W to V, right? So V minus.
Exactly. Exactly right. So it is just going to be V minus S minus W. So this here is CV, and this will just be as it is, V comma T. And now maybe I should. Yeah. So there will be a D, V at the end. Does this make sense? This is so cool. Oh, now it looks as if it's in the. Yeah, yes, it's fine now. Yeah. So I guess let me maybe wait. There's some stuff that happened here. So this is from S to V. No, this was from S to T. Oh no, this is from S to T. This is from S to V. Yeah. So you can again rewrite this expression by considering this V as not the actual time, but the duration. So let me just maybe write that. So you can also rewrite this thing. So yeah, integration from 0 to T minus S. So everywhere you have V, now you are going to write V plus S. So e raised to minus integration of S. Okay, I'm not going to write this as well. What I'm just going to write this thing is P of SWS bar, and instead of V, I'm going to write S plus V. So S and S plus V. So this is the first term. Then you have this row here, which is again from V. So it's going to be V plus S. And here again, it will be S plus V minus S. So you only have V minus W, V plus W here. And then you have P, H, H, V S plus V, comma, T, dV. Yeah. So this would be if you consider V as duration. So again, if you're considering V as duration, your U and all the other stuff will also become duration. So that when you say that you're making this transition at time V plus S, this is just the duration that you have added to S. So not another time that you're adding to S. This is the duration that you're adding to S. And so will be the case here as well. So again, I just hope this made sense to you guys. I know this can be a bit tricky, so you'll have to go through this at least once or twice. So that's it. That's it from my side for today, and I'll see you guys day after. Oh no, let's just do it tomorrow because I'm not going to teach this stuff again, but we'll just look at some modeling and maybe we can just have 1.5 hour class tomorrow. Yeah,
Ma'am,
we'll
can we
have
please have a day off tomorrow?
Okay, all right, let's have a day off. What, today is Thursday, right? Okay. So let's have a day off, and then maybe we could just do stuff in the next lecture. I'll declare when that will be. Okay.
Ma'am, otherwise, like if Isha is okay, or like we actually don't have class on Saturday, Sunday. So if you give us off on Saturday, we get those both days off. It will be a kind of a proper break for us. So if Isha is okay.
Okay, Isha, what do you